All right. Well, good afternoon, everybody. Um, so we finished chapter 1 on Tuesday. So today is the beginning of chapter 2. Um, so we've so far discussed electrostatics, and however beautiful I find Gauss's law is, I think things really start becoming very interesting once things are starting to move. So we're going to take very, very small steps in moving charges around, because if you make a move too quickly, we're probably very easily jumping way ahead in the textbook. So we're going to move them very, very slowly, and we're not going to worry too much about what moving charges do, other than the fact that they experience different electric fields depending on where they are, and they might be accelerating. But what the charge itself might be doing, because they end up generating magnetic fields, we will forget about that for now. We'll only move these charges slowly, and we'll do that. Now, it turns out that just like the gravitational field, the electric field is a conservative field. And because it's a conservative field, it turns out we can ascribe a potential function to any kind of electrostatic configuration. And that potential function is only a function of position, meaning any kind of path you take through the electric field is going to involve an amount of work done either by the field or by you working against the field, and that total work done is going to be independent of the path taken, and only going to depend on the beginning and the end position. So these are all different ways of saying it's a conservative field. Now, what we then therefore need to do is, okay, what does that potential look like? And I'll also try to explain why it's useful to have a potential. And we will do that in a little bit. So this is the beginning of chapter 2. So let me pause it and then take roll, and maybe some questions on chapter 1 if they're here, and otherwise we can move on. So we're going to move charges around. The most simple situation to work with is, as always, a uniform electric field. We will not worry about exactly what the origin of the electric field is. We will just assume that it's there. It's not too hard to imagine situations where you can create a uniform electric field. In fact, we've done a couple of exercises. But you'll see that the principles we will develop will translate well from uniform electric fields to fields of an arbitrary form. So this is our electric field, and now we're going to put a particle here, and use black for that. And I'm going to make this a charged particle. So I'm going to make it a charged particle, and I'm going to say it's positively charged, just for simplicity's sake. We don't necessarily need to use that, but it just makes drawing everything much easier. And so far we've discussed what forces would be acting on this charge, but we have not actually discussed what the result of that force acting on the charge would be. And obviously, if there's a force acting on this charge, it's going to move in the direction that the force is exerting, and making Newton's law to figure out what the acceleration is, et cetera, et cetera, et cetera. Okay, so sure enough, the force that this charge will experience is going to be the Coulomb force. So the Coulomb force obviously is going to be pointing in this direction, and this is our Coulomb force, Q times E. And they're vector quantities. Okay, so now this thing is going to move, and let's say we check back in with this particle by the time it's here. So I'm going to call this Q prime. So after a little while, it's over there. So it will have traveled this path, and if the electric field is the only thing that's exerting a force through the Coulomb force on this particle, there's really no reason to expect this thing to move in any direction other than a straight line. So the a straight line would go from here, and I'm drawing this with green, and I'm going to go through, and it will have traveled this path. Now, the path I'm going to call L, but I'm going to change the way I call it throughout the problem, because we're going to need generalizations. But for now, we'll just have a path L. L has a distance, actually, right? Because it travels from here to there, so it does not have just a just a distance. It actually has a direction as well. So the usual way to do this is to have some kind of an L vector that points from here to there. So the L vector would be, by definition, the position of Q prime. So this is where Q prime is, minus the position of Q. And if you want to be super careful, you can say, well, this is actually it's a difference vector, so we can put a delta here. That's oftentimes a nice thing to do. Okay, so that's the way that we describe a path. It's a vector, points from here to there. And now the next thing we can do is we can ask, well, if we let this go, what's going to be the velocity by the time it gets here? So there are two approaches, and you've seen both of these approaches before. The first approach is to say, well, as I was saying, there's a balance of forces. There's an F QE, and that's going to be m times a, and because this acceleration is the same everywhere, you can just just ascribe a single number to the acceleration, and then you apply that to your kinematics. R of t is R naught plus V naught t of a, and that's your a t squared. And in this problem, obviously, this thing is 0 because it's initially at rest. That's what I said. We are holding it steady. And by suitable choice of coordinate system, we can just change this thing to 0. And then this vector becomes this delta L. So you have your delta L as a function of t, knowing what a is. So not too hard. This is very, very straightforward when the field is uniform, because the acceleration is just a number, and it's not going to change depending on the position. So it works. It doesn't generalize very well, but it does work. So the other approach is this approach that you have probably seen in kinematics as well, and that is that there's a trade-off between kinetic energy and potential energy. So your potential energy in the initial position, so where we were at Q, plus the kinetic energy, Q is equal to, when it's at Q prime, plus the kinetic energy at Q prime. And therefore, we can use deltas to move one of these over, and then we're going to say, okay, so we're going to do delta K is minus delta U, right? Because when I bring the U, when I bring this U of Q over to this side, it looks just like this position, so Q prime minus Q. So we can use this delta, just like here in L. And the same thing with K. We can move the Q over to the Q prime, and then we get this delta K. And obviously, because they're trading, there's a trade-off between potential energy and electric energy. There's a change in kinetic energy. All right, so what is this? Well, delta U is the work done, right? It's the work done. Hang on a second. So sorry, it's minus the work done. I was missing a sign here. Okay, so it's minus the work done in this path. And the work done here is the work done by the electric field. It's not the work done by us. For instance, if we were to move it in the opposite direction, we would be doing work against the electric field, and that would not be this delta W, it would be the inverse. So this is the work done by the electric field. Oops. That's the work done by the electric field. And we know what that work is. The work is usually F times L. And because we've actually defined L as a vector, we can just do delta L vector, and then we can dot that with F. In this case, the F and the L are pointing in the same direction, so this generalization doesn't really do anything. It's just F times L. All right. Now, we know what F is because it's Q times E. So we have a Q times E delta L. And then we have our delta W. Now we have our delta U. So therefore, our delta U is minus Q E delta L. Now it's no coincidence that there's a Q here, because this potential energy change is going to change proportionally with that charge that's moving here, right? Because the work done by the field is going to change if the force goes up, and force goes up with the amount of charge Q. So it makes a lot of sense that this potential energy change is proportional to Q. And just like before, when we were doing a conversion from force to electric field by factoring out the Q, we can do the same thing with the potential energy. And we can introduce a new parameter, and we're going to call this delta V. And we're going to call that delta U over Q. And right now that's minus E delta L. All right, so this is the potential. V is the potential. V is the potential, and then delta V is the potential difference. Delta V is the potential difference. And the units of V are volts. And we use the symbol V. These are the volts that you've seen everywhere. So this is our way into circuit theory. Okay, but before we are off to the races in circuit theory, we have to see, okay, well, what does this do? Okay, so we haven't really done anything. We've shuffled some signs around, and we've introduced this new delta V, and now finally we have a delta V, and we want to say, okay, well, let's get back to the point. Meanwhile, back at the point. How do you get this V? Well, okay, after we've done all this work, we're going to say delta K is minus delta U. Minus delta U is Q times delta V with a minus. Delta V is this integral. So the work is going to look like this. Delta K is minus delta U is minus Q delta V minus Q E delta L. And now left-hand side is 1/2 mv squared. And that's the energy difference, right, initially at rest. So the kinetic energy change is due to the speed at the very end. So solve for V. Oh, there's a minus and a minus. Yeah, there we go. Minus. So delta V and E are related through a minus sign. That's important. Solve for V. So we're going to get 2m Q E delta L over M. See. Final answer. All right. You can plug in some numbers if you want. So for instance, let's call this thing, let's call it 1 nanogram. And let's give it a charge of 10 nanocoulombs. And let's make the electric field 1 Newton per coulomb. And let's do the path length is 1 meter. All right, then our V is going to be the square root of 2Q, that's 10 to the minus 9 plus 1, because it's 10. E is 1, delta L 1. And the mass is 1 nanogram, so that's 10 to the minus 9. So it's the square root of 20, which is something, 4 point something. And that's, of course, in meters per second. All right, so that's how we can solve moving charges problems, or in other words, kinematics problems. This potential is a very handy function. Before we start talking about different electric fields, let's talk about what happens if the path looks a little bit different. So, for instance, if through some means we don't make it go the green path, but we make it go another path. Yeah, blue is annoying, but okay. Somehow we make it go from here to there. So the blue path is another delta L. It wouldn't do this by itself, for instance, because the only force acting on this particle is at this point is the electric field. But for instance, we could put this particle on a ramp, and then the normal force would make sure that it moves it in this direction. And now we can ask ourselves, okay, what is the velocity in this direction? Oh, by the way, I didn't put a coordinate system here, but this obviously is a vector. All right, for the blue path, we would proceed exactly the same way. We would say, okay, the kinetic energy difference is dependent on the kinetic energy difference is depending on the potential energy difference. We can define our potential energy difference in exactly the same way. The only thing that's a little bit different is now that E and dot dl will have an angle. So because E and delta L are not pointing in the same direction, that dot product is not going to give you a cosine of 0. It's going to give you a cosine of something. And that something is this angle. Let's call that this angle alpha. And lo and behold, delta L times the cosine of alpha is the length of this path. So in other words, the velocity going from here to there, velocity change or the potential energy change or the kinetic energy change, all of these are independent of the fact that it's moved in this direction. It's only a function of the movement that it has done in the direction of this path. And that's because of this dot product. And this holds for all positions on this line. So in other words, we can say, you know, from here to here, we always have the same potential energy change. And it's going to be delta V between these two, and it's actually delta V is in this direction. Let me make that super clear. All right. Another way to think about this is not thinking about this in terms of you know, trig and cosines. That is that you can decompose a path like this in two paths. So for instance, you can get from here to there by first going in the green direction and then afterwards going in this direction. And during this direction, the potential is not going to change because of this dot product, because E and that section are going to be perpendicular. So because these potential, this potential difference is not a function of where you are on this dot, on this dashed line, we're calling these things equipotentials. So equi for equal. And there you go. Okay. So so we've done this for a uniform field. Now our next basic building block is the field of a spherical charge distribution. So I'm going to go back to our rather my favorite model. So again, I'm going to make this thing positive just for simplicity's sake. And these are the electric field lines. And of course, it's a vector. And now we can do the same thing. We can say, hey, you know what? I'm going to take a charge and I'm going to put it here in some position A. And there's a Q here. Let's make it positively charged. And now we can ask ourselves, what's going to happen? Well, we know that a positive charge is going to be repelled by this positive charge. So it's going to experience a Coulomb force in this direction. And this Coulomb force is going to, again, be F is Q times E. And then that is going to be M times A. So now you get your acceleration through the electric field. However, this is where we start running into problems a little bit, because this acceleration is going to depend on the electric field, which itself depends on position. So this is going to depend on position, which means you'll end up with having to execute an integral. So kinematics in that sense is not necessarily faster. We're going to use the potential approach, and then actually behind the scenes, there's still an integral at work. But once you've done it once, you don't really need to do it again. Unless I ask you again for a homework problem. Okay, so we go from here to here. And now, instead of doing the this using the work f.dl, we're going to have to integrate f over distance. So we'll do the same thing, except we're going to write this as an integral. So our delta work is the integral. Oops. My hand slid off the paper and made it blurry. And now FDL. So if f is constant, then this is just f times dl. But if it's not constant, then you have to execute this integral. All right. Now, that is Q times E dl vector. And now the potential energy is minus that, and delta V is that over Q. So I'm going to say delta U is minus, same expression, and then delta V is therefore minus E dl. So it looks very similar to what we had before, right? There's an EDL, except instead of having it as a straight up dot product, we have it as an integral. Okay, so if this delta V is going to help us solve kinematics issues, just like here, so we have a delta K, a Q times delta V, all we need to know is what this delta V is. And this delta V, as it happens, is just the integral of E over the path. All right, now we can write that integral. This is not a complicated integral. So E, I'm going to use the K Q R hat over R squared dotted with DL vector. I'm using the K notation because otherwise I get tired of the 4 pi epsilon naughts that you have to carry over all the time. Okay, so that's our basic integral. The path here, the delta L or the DL vector, is going to be in the direction in which the force is pointing, because we're just kind of letting it go and ride by itself. Therefore, that path, this R vector, is in the same direction as the DL vector. So this R hat dot DL, so let me write that down, R hat times DL is R DL cosine something theta, and then this is 1. So having established that, this integral becomes a little easier. And then the only thing that we need to integrate is this R squared. So we finally get a minus K Q 1 over R squared. And now the DL is actually a path in the R direction. So 1 over R squared dr. And we integrate that. Okay, we're almost done. So that's a minus Q. It's a minus again. And now we have to find our bound. So we're going to go from A to B. So that's therefore KQ that's our potential difference. So one thing with potentials that is messing people up a lot often is that we get a potential difference that is dependent on the path that we take, and the path, becomes kind of annoying to always write it like this, and because in a little bit we'll find that again our path, our potential difference is going to be independent of how you get there. You can pick a point somewhere in the middle as a reference where this potential becomes nicer, and then one of these terms drops out. But you have to be really careful with the sign changes. So we'll do that in a little bit. But for now, let's just see what this expression looks like. So let's look at the sign, for instance. So we know that it's moving from here to there. So therefore, the position in, or in other words, R in position A is smaller than the R in position B. So 1 over RA is bigger than 1 over RB. So this term is negative. Does that make sense, that delta V is negative? Question, why is that cosine 0? Because the path and R vector are in the same direction. Okay, so for this path, delta V is less than 0. Does that make sense? Well, yes, it does. Because remember what delta V does. Delta V is the potential change. If that's negative, that means that the potential goes down in this direction. Therefore, also the potential energy goes down in this direction. And that potential energy change comes at the benefit of a kinetic energy change. So the fact that the potential energy goes down means that the kinetic energy goes up, which makes sense because if we hold it here, we let it go, it's going to get accelerated, so the kinetic energy goes up. So this is perfectly fine that it's negative. So that's the potential for this situation, but I'm going to draw on this, and we're doing this with the Nearpod thingy again. And I'm going to give you a couple of paths. So I'm going to put a path from A to C here, where RA and RC are the same. So RA is RC. And now I'm also putting a point D out at R is infinity. And now I'm going to ask you to work out the potential difference for those four situations. So I'm going to write it down here, and then you can enter it. So there we go. And I'll take a picture. I'll make this snapshot bigger. All right. So this is the expression that we came up with for potential differences in a path around a charged object that has spherical symmetry. And it's just the potential difference between point A and point B is the difference between their inverse positions with a minus sign. So if we go instead of from A to B, then we have this expression. So that's KQ 1 over RB minus 1 over RA. And it is indeed less than 0. Some of you saw that correctly. Okay. If we go from A to C, so then I replace my point B with a point C, then in this expression, we get this R of C. And I said that R of A is equal to R of C. So these two factors are exactly the same. So it comes out to 0. Now, if we go from D to A, we need to swap the A and the B and then make that a D. So it becomes A here and then D there. So it becomes K, Q, RA, RD. And now in the limit of this going to infinity, this thing drops out. So we just get K, Q, 1 over R, A. Okay, so now the question is, can we make this a little bit simpler? And we can. So
um, we can take any kind of path. So for instance, from point A to point B, and we can always deconstruct that in paths that are at the same R and paths that are moving radially out. So for instance, if I pick another point, let's say here, E, that's confusing, E, F, Q, point P. Point P. So let's say we go from point A to point P. We can go first in this direction, and then in this direction. And the potential change is going to be solely due to this part, because the potential only changes when you move in the R direction. And in fact, we can do this for an arbitrary path, because an arbitrary path, we can always take a path that is going to the side, and then a path that's going out, where this is dr, and then this would be, for instance, d phi. And then in the direction of d phi, it's perpendicular to the field lines. There's no potential change, so we only have a potential change due to r, and then we always end up at the same potential. So this is this potential difference apparently does not depend on the path taken. In fact, if you want to, you could take this thing all the way to point D, all the way to infinity, and then wait for a really long time, and then bring it back and bring it to point P, and still the potential energy, the potential difference between these 2 points would still only be a function of A and P, and it would not matter that you've gone to the end of the universe and then back again. So that's good. So we can say a couple of things. We can say, well, the potential is path independent. So delta V, path independent. And therefore, that means that if you go from A to P and then back from P to A through another path, as long as you end up in the same position, you will not have a potential difference. So the potential at this point is a function purely of position, not the fact that you could take little excursions and then after a day of long moving around through charged electric field environment and then come back, and then you'll have a delta V of 0. So that means that E is a conservative field. Now, we've only done this for static charges, right? So we've let this thing go. We can let it go, but the rest of the universe didn't really change. But as you know by now, when we were doing Gauss's law, we made this generalization that we can make any kind of static configuration of a random distribution of charges. We can always make it appear as, because in fact, microscopically they are, it is going to be a superposition of electric fields due to all those charges. And because you can go from electric fields to potential through an integral, that's superposition principle that holds for E also holds for V, because it's a linear operation. You're not doing anything nonlinear. So in other words, delta V is path independent not only for this spherical charge distribution, it is for any kind of charge distribution. And therefore also the electric field is not just a conservative field for a single nicely spherical point charge, it is also a conservative field for an arbitrary configuration of point charges. So that's quite a powerful statement. So now I have one more thing I want to talk about, and that is reference. So for instance, the path, I said, let's go from point A to P and let's go through D. Its potential difference from A to P does not depend on the fact that we went to D in between. So let's write that down. So for instance, this is we're going to take a path from A to P, and then we're going to go through point D first, right? So we're going to go first delta V, A to D, plus the potential change from D to P. All right, so delta V, we just split up the path from A to D and then D to P. So this first expression is just the potential at point, is the potential at point D minus the potential at point A. Notice that I have not, I'm dropping the delta here. So if you go from A to D, you need to take the potential at D and then subtract the potential at point A. So same thing here, from D to P, that means you take the potential at point P and you subtract the potential at point D. And now you see that the potential at the point D, I'm sorry, my D's and my P's are looking very similar. Now it looks like a Q. Anyway, so the D, A, P, D, okay. So going from here to there, this thing is going to cancel with this. So I'm getting V, P, minus V, A, and then that is delta V, A to P. And that is identical to here. So we know that a construct like this works mathematically really well if we have some kind of a potential function that is a function of only the position. And we take that potential function and we call it just V, and we're going to call this K, Q over R. So it's no longer a potential difference. This is the absolute potential, except, of course, you can't really use this expression in kinematics problems unless you have a path that takes you from a point, let's say A, to a point P. So this is it's a nice and short expression, and it is the expression that goes with the electric field. So K, Q, R squared, R hat, electric field. You can use these interchangeably, and I'll show you in a little bit how that goes. But you see how similar they look, and that's why it's nice to use this definition of potential rather than this really long potential thing in parentheses. And you can always get this back, because in order to go from potential to potential difference, you just need to take the potential at some point minus the potential at the other point. So this works, and it's equivalent. It's the potential that corresponds to that electric field. All right. So oftentimes when we write a potential and we don't write it as a potential difference, we'll say that R is infinity is the reference point. To be really clear, doesn't really matter too much because you can put the reference point anywhere, but then that explains why that term disappeared, because 1 over R, where R goes to infinity, that term disappears. All right, so so that's the potential. Now, one thing I did not do yet is I did not draw the equipotentials yet. So the equipotentials will be collections of points in space that are all at the same potential. And we know that the potential does not change if you're moving in a path, dl, that is perpendicular to the electric field lines. So in other words, it looks just like this. It's a collection of points that are all at the same distance. And this is a sphere, right? So it's a sphere around around an object. And then the equipotentials here etc., etc., etc. So they're a set of concentric spheres. So these are the equipotentials. All right. Now, now we've established some basic framework. So let me summarize it. So we have to go from electric field to potential, and I'm going to write that as a delta V. It just means that your delta V is minus E dl, some kind of a path. And then we say that V is function of R alone, not on how you got there. And furthermore, therefore, E is a conservative field. All right. So the this is a very powerful concept that we can go from electric fields to potential, and it turns out that it's very easy to go back as well because you just work backwards, right? So if the electric field integral gives you a potential, then obviously the derivative of the potential gives you the field, but then with a minus sign. I'll show you how to do that in a little bit, but before I do that, let's work on potentials with a slightly more complicated situation. So the potential of a dipole. All right, we've looked at the dipole configuration when we were looking at the electric field, and then remember that I said let's not work it out completely because we'll be able to get there faster. So this is our entry into this faster approach. So we'll have a positive charge here, so plus Q here. We'll have a negative charge here. And then they're separated by some distance. And then we're going to ask ourselves, okay, what is the potential at some arbitrary position V? Now, this problem has cylindrical symmetry, right? Because these two charges are on a single line, which means that we can rotate the entire problem around this axis and it will be identical. So this two-dimensional cross-section is perfectly valid as long as you remember that this point V could also be rotating around it, and as long as it stays at the same height and the same distance from that axis, you're fine. So we're doing a 2D projection of something that is intrinsically 3D, but you should all be quite comfortable with that right now. All right, now let's see how we do this. So the potential at this position will be the potential due to this charge and the potential due to this charge, and we're going to write it as an absolute potential, not as a potential difference, using again the convenience that we can always get to differences by just taking this voltage and then subtracting two values for two different points in space, and then you'll have a potential difference. So there is RV of Q plus RV of minus Q. So didn't really do anything. I just said the obvious. So now this is K Q over R, I'm going to call this Q, plus K Q, but this is negative, and this is R minus Q. So you see that there's a K and a Q in common. So that's going to be K, Q. All right. Now 1 over RQ minus 1 over R minus Q. Okay. Now we need to be really careful. This is where it gets a little tricky. So we need to ask ourselves, what is this RQ really? And it is the distance between the location of this charge Q and the point where we would want to know the potential. So RQ is a vector that points from here to there. And R minus Q is a vector that points from here to there. So let me write that. So this is RQ. It's a vector, even though we'll use it in scalar notation, but that's okay. And now minus Q is in this direction. Oh, not straight. Okay, this is R minus Q. But that's not a very useful thing to have, an expression based on these two, where they have different locations, because we would like to have it as a function of some kind of a coordinate system that we can define. And that coordinate system, let's pick the origin for that. Let's pick that here. And then let's pick the position vector as usual. Like this. And let's pick the z-axis in this direction. So z goes in this direction. And then that means, well, let's call this x. And again, this x, it can rotate around it because we have cylindrical symmetry. So I'm avoiding the use of r because we have enough r's in the problem as it is. Just r, we don't need another r. Okay, so let me get here. All right, so I'm going to call this distance d. And I'm going to call this distance also d. With the note that at some point I'm going to change this. I'm going to call this total distance d. It's just that in this problem, we'll get a lot of 1/2s all over the place, and it just gets tedious. So let's not do that. So distance is d. They're in the z direction. So your assignment for the next couple of minutes is write down RQ as a function of d and regular r. So let me write this here. All right. So the couple of notes about this. The position at this point is r. That's the r vector. Now we have the potential at this point due to this charge being a function of this RQ, the green RQ. But the RQ obviously has a smaller z component than the position factor here. So in other words, if you want to go from here to there, you would have to go from here to there and then down again, and you would get the same vector. So in other words, this RQ is going r minus d times z hat. And similarly, for the minus q, it's r plus d times z hat. Now, the the thing we actually need is the magnitude of this. Now, there are several ways to approach this problem. There's, you can run around with cosine rules and everything on the on this problem, and I believe that's the way I did it in the book. But let's try to do a slight shortcut. So I'm going to now say, well, therefore the length of our cube, that's going to just be the R vector, which has an X and a Z component, but the Z component is smaller by D. So it's going to be Z minus D squared plus X squared. And now the R at minus Q has the same kind of construct, except this Z component needs to be raised by a D. So this is Z plus D squared plus X squared. And this is the thing that we will put into this equation. So just for completeness sake, I'm going to write it once, and it's going to look terrible. Just bear with me. So Z plus D squared plus X squared, and that minus 1/2 minus, okay, other Z, I'm sorry, messing up my signs, minus. So that's the potential in all its glory. It's not a very pretty expression, and there are usually a couple of things that we do to simplify things. So, for instance, we could ask ourselves, okay, what's the potential on this axis? So if that's what you want to know, then the Z component is 0, so put in 0, then you have just a minus D squared, and then you have a plus D squared, and then the rest of the expressions are the same. You subtract two equal expressions, you're going to get 0. So in other words, the potential here on this is 0. The potential over here, when x goes to 0, is going to be Z minus D squared, and then the square root, and then inverted it. Z plus D squared, square root, and inverted. So it's a simple subtraction of 2, 1 over Z D, Z plus D and Z minus D terms. The biggest mess you end up with is when you're sort of in the middle. So there's a very common expansion that we do, and that is far away. And far away in this case is a little bit hard to quantify because we have a position that we can change based on x, and we have a position that we can change based on z. And we want to say it's far away based on the scale set by the d in the problem. So we want to say simultaneously z is much larger than d, and x is much larger than d. So let's see what we can do with this expression. So we're going to have a z plus or minus d squared plus x squared. And now this we can write, oh no, sorry, still exact, as z 1 plus or minus d over z squared plus x squared. And now for small d over z values, we can expand this. This becomes z times 1 plus or minus 2 d over z plus x squared. Oops, there's a squared missing here. And now we can factor these in. We can say it's z squared plus x squared plus or minus 2 d over z, which again, we can expand. So because we're going to have to take the square root, so we want to take the square root. I might as well start on a new piece of paper. I was hoping.
So we have this expression. This expression is the one that we need here before we take the square root and the inverse and then subtract the terms. So now what I want to do is I want to see what happens with these terms and can I simplify them further if I take the square root and the inverse. So I will need to calculate the following. So the z squared plus x squared plus or minus 2dz, and then I will need to take a square root and inversion. And but before I can do this expansion for small distance, I need to write it as a 1 plus or minus something small. And now, at the same time, let me make a simplification. This is r squared. All right, so this is r squared times 1 plus or minus 2dz over r squared, and then the whole thing is raised to the power of minus 1/2. Now the minus 1/2 acting on the r squared just becomes 1 over r. So that's easy enough. That's not an expansion, but the second part is going to force us to make an expansion. So that's the minus 1/2 means that we pick up a factor minus 1/2 in the Taylor expansion. So that's minus 1/2. So we have a 2dz r squared. Okay, and now we have this term. And we're going to subtract one term where this is a plus from the other where it's a minus, because so this one originally was a minus, but when I did the Taylor expansion, we picked up a minus. So that term becomes the term with a plus. And I'm going to subtract the term with the minus from that, which means that this thing is going to cancel. And I'll end up with the following. So V, okay, Q. And I'm going to drop this term, but I'll have another factor r here. So I'll have a 2dz now over an r cubed. Okay, this still looks a little tricky, but we can simplify it a little bit. I was saying earlier that this 2d, we were going to change it later, and this is the moment. So I'm going to say 2d now becomes d. So d is the distance between, d is now the full distance between q and minus q. All right, now, next thing we do is we say d times z is actually the projection of the coordinate on the z-axis. So d times z is actually the d vector, sorry, 2d 2d projected on the position vector. So using this and this factor 2, we now get a potential for the dipole, which is going to be k q d r over r cubed. And now I'm going to take the r vector over r cubed. And now I'm going to write that as k q r d r hat over r squared. So there we go. It's the potential of a dipole. far away. There you go.
We've developed this new thing called potential. So I always like to go back to my concept map, and we'll do it this way. So we'll say, Q generates an electric field, and then we have a Coulomb force. Oops, I usually use a small q. And then a flux is a derived thing that we can always get from EDA. And now the Q goes to E by DE is and then we had a shortcut using Gauss's law for situations of a high degree of symmetry. And this is Maxwell 1. And that said that the flux is EDA is Q enclosed over epsilon naught. And now we have a new concept, potential. And we could go from electric field to potential, and we can go from potential to electric field. So EX is minus dV dx, or V is, delta V is, And now the final thing is we can say something about the fact that the electric field is a conservative quantity, because we know that if we go in a closed path in the circuit, the potential difference ends up being 0 if you always come back to the same position. And that, ladies and gentlemen, is a relation between the E and the V quantity that says that E dl for a closed path around some kind of a circuit is going to be 0. And this is Maxwell 2. And this is an expression that guarantees that the electric field, or encodes that the electric field is conservative.